Okay, so let me then begin by briefly recalling what we described last time. So, review of StatMech. So, we work with the microcanonical ensemble. So, omega was defined so that this times delta E is the number of quantum states between E and A plus delta E. Given this, we define the entropy S E N V as log omega. I am setting the Boltzmann constant equal to 1. This is the unit we will be working. From here, we define the densities. Let me write those first. So, small s was the entropy density, rho was the energy density, and small n was the number density of particles, N over V. We also define beta, which is 1 over T, as del S del E, mu as minus 1 over beta, del S del N, and P as del S del V. And then we say that of the various variables that characterizes the intrinsic property of the system, which are S, rho, N with densities, and P and mu. So of these, two are independent. Because there are four relations between the two that we wrote down. So the four relations were, first, S is given as some function of rho and N. That's basically this equation. Okay, you define S as log omega, and omega is known as a function of E, N, and V. So from this, you calculate the small s as a function of the energy density and the number density. Okay. Then we had an equation which told us that small s is P plus rho minus mu n over T. And then we had two more, 1 over T is equal to del S del rho and minus mu over T is equal to del S del N. So these 3 and 4 are basically these equations, except that we write in terms of the densities rather than the extensive variables S and N and E. Okay, so using these 4 equations, we can relate 4 of them to 2 of them. Okay, which 2 you choose to be independent, it's up to you. Now, one of the problems of working with microcanonical ensemble, okay, even though it's the most physical one. But the problem of working with microcanonical ensemble is that calculating omega is not very easy, usually. Okay? Because here we are asking to count states, okay, with constraints, right? The constraints that we are imposing are the total energy is between E and E plus delta E, total number is N. So what is normally done is to work with grand-canonical ensemble and calculate the thermodynamic quantities from there, because that's easier. So let me define what grand-canonical partition function is. So grand-canonical partition function Q mu beta E. Okay, so it's naturally described as a function of the variables mu and beta. This is given by sum over n prime integral d prime omega e prime n prime v, and then e to the power minus beta e prime plus mu n prime, mu beta plus beta mu n prime. So basically what you are doing here is that you are not restricting the total energy to be any fixed number or the total number of particles to be any fixed number. You are integrating over all energies, summing over all possible numbers of particles, but you are putting some weight factor which depends on the energy and the number of particles. Okay, the weight factor is minus beta e prime, and the for the weight factor for n prime is beta mu. The reason that it's useful is because of thermodynamic limit. This receives contribution only from some particular value of e prime and n prime. So in the thermodynamic limit, only one e prime and mu prime dominate. This is dominated by the value of e prime and n prime, where the integrand is maximum. And that maximum, the place where the integrand is maximum, we'll call E and N. Okay, E prime was the integration variable, N prime was the summation variable. But we say that this is dominant at some particular value of E prime and particular value of N prime. So what are you maximizing? So this integrand is basically e to the power s e prime n prime v minus beta e prime plus beta mu n prime, right? Because omega is e to the s, that's the definition of s. So you have to maximize this. You have to maximize this. And that gives del S del E plus minus beta equal to 0, and del S del N plus beta mu equal to 0. Okay, here I have replaced E and E prime and N prime by E and N, because these are the equations for the maximum. Okay, so E and N are the values at which the integrand becomes maximum. Is this okay? And you recognize that these equations that we have are the same equations that we have here. Beta is del S del E, that's the first equation. And beta mu is minus del S del N, that's the second equation. We also have some other equations from, get some other equations from here. So for example, if we calculate del Q, del mu, del say beta. If you take del Q, del beta, in this you bring down sum over n prime integral d prime. Let me write, this is omega is exponential s, so s of e prime n prime e prime minus beta e prime plus beta mu n prime, and the derivative with respect to beta brings down a factor of e prime. Minus sign. I'll put a minus sign on this.
Okay, won't there be a mu in prime also?
Yes, you are right. E prime minus mu n prime. Okay? But now we know that this quantity is peaked at E prime equal to E and N prime equal to N. Right? And it's peaked very, there is a sharp peak in a thermodynamic limit. And that basically means that this E prime, you can set E prime equal to E and mu N prime equal to N in this argument. Right? So this basically becomes E minus N, E minus mu N times Q. Because I can set E prime equal to E, mu N prime equal to N, and take this outside because E and N are of course the fixed numbers. So that we get by extremizing this. So we learn that E minus mu N is minus del del beta of log Q. Okay, it's 1 over Q del beta, so minus del del beta of log Q. Similarly, you can verify that N is del del mu of log Q. Let's see, del del mu of log Q, so it's not N, it's beta N. If you take mu derivative of Q, and you bring down beta times N prime. And then again you use the fact that it's maximized at N prime equal to N. Okay, so you can replace it N prime by N and bring it out. Okay, so that's what gives this equation.
How do we ensure that this peak is very short?
Okay, in a thermodynamic limit, one can check in all systems that this peak is very sharp. Right? That's the place, that's only then you can talk about thermodynamics. Right? That as V goes to, so basically what happens is that all of these, right, scale with V. Okay, because S we know is extensive, it's scaling with V. E prime goes as V. If you double the volume, E prime doubles, right? So if you take V to be very large, right, then what happens is that this V comes out and then there is a function. Right? That function, if it has a maximum, right, you are multiplying that function by V, right, which is a very large number. So that makes a maximum sharply peaked. Right? So that's the thermodynamic limit. Are there other questions? Okay, so these equations, in fact, you can. Okay, I'll do that. Let me just say one more thing. So this, so far we have introduced most of the variables that appeared earlier, okay, and you recognize that these equations that we have here are the same ones that we had earlier. So the only variable that we have not introduced so far is P. Right? So let me now define P in a grand-canonical ensemble. And the definition is in fact very simple. P is 1 over beta V log Q. This is the definition of pressure. Okay, we'll see that it agrees with the other definitions in the current ensemble that we give. Okay, so using this definition, I can rewrite this equation slightly differently. So if I divide by V, I get rho minus mu n is equal to minus del beta of 1 over V log Q, but that's beta P. Okay, so this way it's a relation between only the intrinsic variables. Okay, there is nothing here scales with V. Similarly, this one, if I divide by V, I get beta n is equal to del mu, again 1 over V log Q, that's beta P. Is this clear? Okay, so let's check that this agrees with the earlier definition. Okay? Because these are important because you are going to use these to calculate various thermodynamic quantities, right? Because Q is much easier to calculate, as I said, the grand-canonical partition function. So we better check that what we are calculating is the same as what we had introduced earlier. So let's look at the definition of Q again. So Q receives, or the integrand I can also write this way. So this integrand, as we have already said, is sharply peaked around some E and N. Okay. So then Q will be given by e to the power S E N V minus beta E plus beta mu n times, let's call it some delta E. This is the width of the peak. So Q roughly is this much, okay, because the integrand has this value, times the width over which the peak exists, right? This is a rough estimate of what Q is, up to a multiplicative factor of order 1, okay, which you don't care because you are looking at log Q eventually. Is this clear? Q is the integral of this, right? And all I am saying is that this integrand is sharply peaked, okay, around E and N. Okay. The value at the peak is obtained by substituting E prime and N prime to be E and N. So the total integral is the value of the integrand times the width. Okay, that's the rough estimate. Okay, up to multiplicative factor of order 1. So that's what I wrote here. So then P, according to this, is 1 over beta V log Q. So let me write beta P. Beta P is 1 over V log Q. So 1 over V times S minus beta E plus beta mu n plus 1 over v log delta e. But this is negligible because v is going to infinity. Thermodynamic limit is v goes to infinity, right? So this I can set equal to 0. So this gives you s minus beta rho plus beta mu n.
So for some p, this delta e tends to 0, then ln 0 by t.
Yeah, but it still goes to 0 logarithmically, right? If you can estimate the width, the delta e, right? It goes as log of v, log of 1 over. Okay, so log of v over v still goes to 0 as v goes to infinity. Right? So you don't worry too much about this part. This relation you can easily verify is the same as this relation. Okay, so this definition of P agrees with what we gave for microcanonical ensemble. So based on these equations, we can again check that we basically have 4 independent equations among the 6 variables. So what are the 4 independent equations? One is this one. One is this one. Okay. These 2 are equations involves rho, mu, n, p, beta, etc. Then this one. P. Okay, these are of course universal equations. Doesn't depend on the system. The third equation, or the last equation, is the expression for p itself. So p you calculate. Okay. Log q is given as a function. These are of course integrated, so it's given as a function of beta and mu. Okay. So this is some function of beta and mu. Let's call it g. I had called the other function here, right? So these are 4 equations.
So here this will act as an equation of state.
This will act as an equation of state. This function g is what captures equation of state.
But sir, we have already used this equation by circuit.
By which equation?
This one, the q equals to sum over n times this one, the last. No, this one, this definition of q in equation 3.
Yes, this one.
Beta p equal to s minus.
The 3 are, I think the 3 and 4 are same equation because we are using the same definition of q.
The other.
Yeah, but the point is that let's look at these equations. See, this equation is a relationship between these various variables, right? Which is independent of what system we are considering, right? So this equation, okay, these equations are independent. That you would agree because this one doesn't involve rho. This one has rho, right? So these equations are independent. This you can think of as a definition of rho. This is a definition of n in terms of other variables. Okay. This is a definition of s. This equation, right? That's again a new variable. Okay. So this tells you rho, n, and s in terms of beta and p. These equations, right? Beta, p, and mu. Okay. This is the last equation which relates p to beta and mu. Right? So these are all independent equations. Right? So this equation, okay, so let's start with this one. This gives you n in terms of beta, mu, and p. Once you determine n, this gives you rho in terms of beta, mu, and p. Right? This one, this is the only equation where s has appeared. So this gives you s in terms of beta, mu, and p. And finally, this one gives you p in terms of beta and mu. Right? So these are 4 independent equations. Here, of course, again you had 4 independent equations but here the way it was organized, everything was expressed in terms as a function of rho and n. Okay, but that's just different ways of representing the equations. So both from the microcanonical and the grand-canonical point of view, you can see that you have actually 2 independent variables that characterize a system in thermal equilibrium. is this here, and you can derive these set of equations from here. Okay, once you establish certain relation between G and F. Okay, so it's not that we have 8 equations, right? We have really 4 equations because these are equivalent to those. Okay, so before I go on, I'll give the result for the ideal gas because that will be used very heavily. Result for the ideal gas. Okay. Now, when I say free ideal gas, it's with qualification because free in the sense that you can ignore the effect of the interaction between these particles in computing the partition function. That's what I mean by free. Okay. Nevertheless, okay, we are assuming that the interaction is sufficiently strong so that thermal equilibrium is established. Okay. Because if there is no interaction, okay, then there will be no thermal equilibrium. Right? So even ideal gas, okay, is not fully non-interacting particles. Right? That's not what ideal gas means. Right? Ideal gas is when the interaction is small enough so that you can ignore its effect on the partition function. Nevertheless, it's strong enough so that thermal equilibrium is established. So with that, the result is log Q is, I'll write the expression for bosons and fermions together, minus plus V over 8 pi Q times integral 0 to infinity 4 pi a square dk log 1 minus e to the minus beta e of k minus mu where e of k is just square root k square plus mu square, k square plus m square. Okay. M is the mass of the particle. Okay, so Ek is basically the energy of a free particle of mass m carrying momentum k. Here, I think there is a minus plus. Okay. So the upper sign is for the bosons, lower sign is for fermions. Okay, so for bosons, it's minus here, minus here. For fermion, it's plus here, plus here. So this, according to the equation here, this is the result for V beta P. This is the result for V times beta times P. It's okay? Okay, so from the grand-canonical, in the grand-canonical ensemble, we will normally work with beta and mu as the independent variables. Okay, and try to express everything in terms of beta and mu. This calculation is straightforward. I mean, you have to do some counting of states, but that counting is much easier than counting in the microcanonical ensemble.
So what is the statement result for V beta P?
This is because log Q is V beta P, right?
Equal to.
So this is equal to.
Okay.
So log Q, this is equal to V beta P. That's what you are calculating. So now with this, you can write down the expressions that are given here. So n is 1 over beta del mu of beta p. Right? And mu and beta are independent variables, so it's basically del mu of p okay, and you can calculate that from here. So this gives you 1 over 8 pi cube okay, so what we did here was
So another
there is some betas which is
No, that will be cancelled.
yeah that will be cancelled, that's right, because there is a 1 over beta coming from here, right? So you are taking a derivative with respect to mu, right? So you get 1 over this times the derivative of this, right? And that's what I have written here. Derivative of this will bring down a beta, right? But that beta gets cancelled because we have to have a 1 over beta, right? P is 1 over beta times this.
So how is the outline for the computation of this partition function? Is it kind
This partition function, basically you think of this as a set of particles in a box, right?
kinetic theory?
Not kinetic theory, just take particles in a box, a periodic box, right? The energy levels of the particle you know, single particle energy levels, right? Then you try to basically look at, fill the energy levels, right? And count the energies, right? For multiple particles, right? For bosons and fermions, you know how to fill the energy level.
Density of states kind of thing?
Yeah, you use density of states, but you can also directly just do a counting. Right? So you use the density of states to fill the energy levels, taking into account the fact that for bosons you can fill the same energy level many times. For the fermions you can fill the energy level only once, right? 0 or 1 once, and then you put the weight factor of this e to the minus beta a plus e to beta n. We don't restrict e or n to be some specific numbers, but just put this as weight factors and sum over all possible energy levels, right? And that's what gives us this expression over here. So rho you can calculate from here, and this is given by 1 over 8 pi cube times integral 0 to infinity 4 pi k square. Basically, I think you get this whole thing multiplied by E of k. Separate this out. So later on we are going to make use of this formula and take various limits. Okay, for example, what happens in a relativistic limit, what happens in a non-relativistic limit, and so on. But this is general formula, which is valid for both relativistic and non-relativistic particles.
But this EK,
Yes.
that is relativistic, right?
Well, if you take k to be very small compared to m, then you recover the non-relativistic formula. Right? So this is general, right? You can either take K to be very large, in which case it's high ultra relativistic, or take K to be very small, in which case it's like non-relativistic.
I think then you have to subtract the m square piece to get the non-relativistic.
No, we will not subtract the m piece. This is the correct formula.
So you will take the rest mass if you take non-relativistic limit.
Yes, we'll take the, well, we'll not, if you take strictly the rest mass, right? Suppose you just replace Ek by m,
Right.
then this integral is divergent,
Right.
right? So you certainly cannot take this to be rest mass, right? You have to keep the next term
Right.
Yes, plus.
so that you get a convergent integral, and then you can make that approximation. Okay, so you cannot directly set in the integrand the best approximation, right? Where you set k equal to 0, okay, because that's a divergent quantity.
Is this also valid for massless particles?
This is valid for massless particles. So you can set m equal to 0. The same formula is valid. Okay. The only other thing you have to keep in mind that this formula is valid. This formula is calculated. This formula is valid if there is one state per particle. One state per particle. If we have g states per particle, then multiply by g. Okay. So for example, photons have two helicity states. Right? So for photons, we have to multiply all of these by 2. Okay? Basically, this log q gets multiplied by 2, and as a result, these also get multiplied by 2. Okay? If you have a formula, electron, for example, right? Electron has two spin states, right? Spin up and down. Again, you have to multiply by 2. For scalars, there is only one state, so there is no multiplication. Is this okay? So far we have been working with systems which have only one kind of particles. Okay, all this formula that I wrote down, okay, and even the earlier formula, okay, they are valid for when you have system with one kind of particles. Okay, because n was the number density of that particle. Okay, m that appeared in the formula for Ek was the mass of that particle. But we will have to deal with a more general class of systems, okay, where you have a mixture of many particles. Okay, that's what happens in cosmology, right? In the early universe, okay, typically you have a mixture of many particles, not just one kind of particles. So we have to ask what happens when you have mixture of many particles, mixture of many kinds of particles. And again, we will assume that each particle is described by a free Hamiltonian. So the total Hamiltonian is basically sum over the free Hamiltonians of individual particles. But there is a small interaction part. This is small, not to contribute to partition function. Contribute to partition function, but large enough to cause thermal equilibrium. So in this case, we can have log Q as sum over I log Qi. These are the contributions from individual particles. Contributions from individual particles. So for each particle, each species of particles, you can introduce all these variables Ni, Si, rho I, beta I, mu I, pi. Okay, just for each of them you use the corresponding Qi to calculate this. But if we have thermal equilibrium, that means that beta I must be equal to beta J for all j. That's a condition for thermal equilibrium. So number of variables, if we really had completely independent systems, the total number of variables would have been twice the number of components. If there are k components, each component has 2 independent variables. So there will be 2k independent variables. Okay? But because of these equalities, there are k minus 1 relations between these k beta i's. Only one of them is independent. So the total number of independent variables now becomes, instead of having 2k, you get 2k minus 1. Because one relation among all these variables. Sorry, not 2k minus 1. 2k plus k plus 1. Right? Because k independent mu i's and 1 temperature. Is that clear? So thermodynamics is determined by k plus 1 variables. Yes.
This approximation of considering just enough interaction to allow for thermal equilibration, this seems to be sort of a generic first approximation to means understand thermal equilibrium, but not interactions that can perturb the system away from equilibrium. Is that it?
Not away from equilibrium. Even in equilibrium, if you have sufficiently strong interaction, right, you can deviate from ideal gas.
Okay.
Right? So you are not allowing the system to deviate from ideal gas. Right? It's like if you have, say, a gas of particles in a box, right? You normally use ideal gas approximation, right? No interaction, and then you can start using corrections, right? Like you using a cluster expansion or something, you can get, instead of PV equal to nRT, you can correct equations of motion by van der Waals equation of state and so on, right? Those are the effects of interaction. Okay? So we are ignoring those kinds of effects. Okay? But at the same time, if we ignore all interactions, then the system never thermalizes. Right? So it's because particles are completely free, right? They never exchange energy. So we are working at the same level, that we have multiple components. Each of them thermalize and thermalize with each other. Okay, that's why you need this interaction term between these components. But we ignore their effect on the partition function. Right? No van der Waals kind of corrections.
But in early universe,
Yes.
this approximation should be.
Yes, so you can check at every stage whether this approximation is valid or not. And for most part of the early universe, this approximation is valid. Right? The densities are dilute enough so that you don't have to worry too much about deviation from ideal gas. But you are right that if the density becomes too big, right, then of course you cannot use this ideal gas approximation. Yes.
For ideal gas, we can say that there are elastic collisions. But for a photon gas, is there collision between photons?
No.
Then how photon gas is in thermal equilibrium?
Well, because photons can interact with other particles. So photons don't directly interchange energy, right? At least not to lowest order. But if the other particles in the system, it can interact with them, right, and thermalize. So suppose you have a gas of photons and electrons, right? Then the photon will interact with the electron, and the electron so can transfer back and energy back and forth, right? So they will together be in the thermal equilibrium.
So there has to be some other type of.
There has to be some other kinds of things. In a if you normally do black body radiation, right? It's the interaction of the walls which cause this transfer of energy, right? Not directly the interaction between the photons. Now, given this, you can ask why CMB are in thermal equilibrium. There, of course, there's no wall, right? And there are no electrons that the photons are interacting with. And this we had discussed earlier, right? You remember, I don't remember why CMB is shows black body spectrum. It shows black body spectrum because early, at some point in the history of the universe, it was in thermal equilibrium with other systems. After it decoupled, it's not in thermal equilibrium anymore. But what we had seen is that the Planck distribution law scales with the expansion of the universe just by saying that the temperature falls as 1 over A. Right? We will try to do this again in this class. But if we just start with the Planck distribution, okay, which is basically this formula. This formula, this is the number density distribution, this is the energy distribution. Okay, for relativistic particle, you say m equal to 0. Okay. And then just say that we put this radiation, okay, in an expanding universe. Okay. How will the distribution change? Okay. And what we have seen is the distribution will change as if beta just gets scaled by A. Okay. The temperature falls as 1 over A. Okay. So even though the photon decouples from the system, it's sort of no longer in thermal equilibrium, okay, either with each other or with anything else. Okay. It continues to display black body spectrum simply because the black body spectrum remains invariant under expansion of the universe. But photon gas by itself cannot be in thermal equilibrium because photons don't interact strongly. Well, of course, there is always some interaction because photons do scatter, right? You have the box diagram. But those interactions are very small. They are not strong enough to bring this into thermal equilibrium. The photons do scatter by diagrams like this, right? Okay, but this has 4 powers of coupling constant, right, which is very small.
Sir, and in the very early universe, it was only a gas of photons.
No.
Very high energy photons.
No. Because there will be gas of electrons, muons. Right? See, if it's a very gas of photons, right, it will produce electron-positron pair. Right? A gas of photons can, produce E plus E minus pair like this. Right? With time going up. So, gas of photons in thermal equilibrium at very high temperature, right, will automatically also have electrons and positrons and everything else that it can produce. So the early universe was, filled with a lot of particles. Okay, and we'll see what happens as the temperature comes down to all those particles.
So whenever the species decouples from the rest of the particles in the system, so then it is out of thermal equilibrium. So then can we use this only 2 variables out of these 6, or
Well, you used it just because a thermal distribution remains thermal under expansion. Right? So there, it's not because of the fact that there is equation of state, right? Because it's not in thermal equilibrium, right? So there is no relation with. So just the thermal equilibrium will not tell you the relation between P and rho, for example, right? But because the spectrum remains unchanged, except for the scaling, the relation between P and rho continue to hold. So there is today, for example, the reason that we have P equal to rho by 3 for CMB, right, is not because it's in thermal equilibrium, right? and it has an equation of set P equal to rho by 3. But because it was in thermal equilibrium early in the history of the universe, and because that distribution remains invariant except for this overall scaling, the P equal to rho by 3 continue to hold. Is this clear?
So the only effect of expansion that is coming in that the scaling of beta.
Yeah, when the gas decouples. When it ceases to be in thermal equilibrium, right? And if it's a relativistic gas, okay, then it basically the only effect that you feel is that the beta changes.
Okay.
Okay, but that's because of the specific nature of the distribution, right? You can check that the distribution formula, the formula that you have here, right, under expansion, okay, basically preserve its form, okay, except for the scaling of beta. Any other question?
Could you repeat how the k plus 1 number of variables?
Okay, so to begin with, each component had k betas and k mu's. Sorry, each component had one beta and one mu. Right? So there are k components, so k mu's and k betas. Now we are saying that because of thermal equilibrium, all the betas are equal. So there are still k mu i's, but one beta. Right? That's why k plus 1 intrinsic thermodynamic variables.
Sir, as universe expands, the temperature also falls down.
Mm-hmm.
So at any time we can't say that the system is in equilibrium because temperature is also changing. So
Yes, so as I described last time, that you have to decide whether the thermal equilibrium is a good approximation or not. Right? And that is decided by asking whether the number of scattering that particles have in one Hubble time, whether it's much larger than 1 or much smaller than 1. Right? It is true that as the universe is expanding, the temperature is changing. Right? But if the particles interact strongly enough so that each particle scatters many times within one Hubble time, then it's a good approximation to say that the universe is locally in thermal equilibrium at each instant of time. Right? But if that's not the case, right, then you have to use other approximations that they have actually decoupled from each other. Okay, and again we'll see this in many examples as we proceed. Okay, so let's now do a quick counting of in cosmology, because so far I have not put it in cosmology, right? This is just thermodynamics. So let's just put it in cosmology and see what kind of counting we have. So in FRW cosmology, the number of variables now is A, right? That is still there, and then mu1 to mu k and t. These are the independent variables. Right? Once you know these, you can calculate p and rho for each of these. Okay. Cosmological constant I am not counting because that's just a constant. Okay, as you saw, that energy density is separately conserved, so that's just a constant which I'll put in there. Okay, that you are not counting as a variable. So this gives you k plus 2 variables.
Cosmological constant will affect the AI.
It will affect the AI. So in the equation, of course, you have to put the cosmological constant, but because it's not changing as a function of time, right? It's just a parameter in the theory, right? So that's why you don't count it as a variable, right? You don't have to worry about its evolution because it's d dt is 0, right? So we don't. That's why I'm separating out. Not that they will not appear in the equation, right? But it's known what will appear in the equation. Is that clear? So right now we are not counting cosmological constant as a separate component because rho lambda and p lambda are just constants. So this is k plus 2 variables. How many equations do we have? So first you have the Friedman equation, number of equations. So we have a naught over a square plus a over a square equal to 8 pi g over 3, and then you have sum over I equal to 1 to k rho I plus rho lambda. Okay? These are all given in terms of the mu's and p's. Okay, the y's are not independent variables. So this is one equation. Then you have the overall energy conservation, d dt of sum over I rho I a cube equal to minus 3 a square a dot sum over I pi. So here I can include only the energy density and pressure from the physical components, leaving out the cosmological constant, because that's constant by itself, as you saw. Right? So that's this equation. So you have two equations. Right?
Last equation represents the conservation of energy.
Conservation of energy. This is coming from d mu t mu nu equal to 0. Right? And I have used the fact that d mu t lambda mu nu is automatically 0, because that's d mu g mu nu. Right? So I have separated this out. Right? This sum I have not included rho lambda. I could have included rho lambda and p lambda on both sides, but this will make no difference, right? Because that's satisfied by itself.
So the right side goes 0 in rho I plus
Rho lambda. Here you have to include rho lambda. Right? This is a full Friedman equation, or everything contributes. So we need k more equations. Right? So what are those k equations? Equation of state we have already used up. You see, only because of equation of state, right, we can say that rho I is known as a function of mu's and p. Right? So equation of state is of no help, right? I mean, last time we were doing the counting, right? The difference here is that we have now introduced some new variables mu's, which you didn't see last time. Right? K new variables. So we need k equations.
So what is the difference in the last time and this one? Can you repeat?
Last time we didn't have the mu's, right? Somehow the mu's, for simple systems that we are dealing with, for radiation mu was 0, right? And for matter mu didn't apply. Mu didn't enter anywhere because of the number density, right, was not relevant for the equation of state. Friedman equation didn't have the number density, right? But that's not true in general, right? In general, these rows will depend not only on t but also on mu. Right? So that's why mu's have entered in the equation now. So you have to somehow get k more equations to be able to solve these equations.
This is in thermal equilibrium, not in independent conservation law.
Which one? Yeah.
This relationship
Yeah.
in thermal.
Thermal equilibrium. Exactly. If you had independent conservation laws, right, there will be k minus one more equations here, right? But also k minus one more variables, because pi's are all independent now, right? So that missing number k will not come from there. Right? So the missing number k is somewhere else.
It's like if we consider the matter particles to be at 0 temperature kind of thing, then T will go, or if we consider radiation, then all the mu's will be 0.
Yeah.
This kind of approximation we used when we
Yeah.
earlier
Because that's why mu's didn't appear.
in the
Right?
yeah.
But now the mu's have appeared, right? So somehow we have to look for some new equations which will give that information. So the mu equation basically will come from a fact that is hidden, okay, but it's there. See, this assumption that mu's are all independent. Okay. This is true only if the number of particles of each type is conserved separately. Okay, if the particle number is not conserved, then mu's are not independent, right? Like just like if you have a single system, if the particle number is not conserved, then mu is 0. Okay, so you have implicitly assumed that the particle numbers of each species is conserved separately, right? In treating the mu's to be independent.
That's the n is not there. The number density is not important there.
No, it is important because if mu, if the number density was not conserved, right, then you didn't have to put this as an input parameter. Okay. Now the point is, we are assuming that the number density of individual spaces is conserved. Okay. Only then the mu's are all independent. Okay, we will do the more general case later. But if it is true that the number density of individual spaces is conserved, then there will be conservation equation for the number densities, right? Not for energy. Energy is already used here. Right? There will be conservation equation for the number densities. Right? So what are those conservation equations? It's d mu, gi mu equal to 0. Right? Just like d mu, t mu nu was 0. Okay. What is gi mu? Gi 0 is basically ni. This is the number density, right? Number of particles of ith type. And gi vector is 0. Okay, that's why isotropic. Okay, it cannot go in any direction, right? All directions are the same. So gi vector is 0. Okay. And I'll leave it as an exercise to check that if you put it in the FRW metric, this just says that dVt of ni times a cube is 0. Okay, ni falls off as 1 over a cube. That's understandable, right? Because it just says in a given co-moving volume, total number of particles is fixed.
Sorry, can you explain what is gi mu?
This is the current. This is the core current for the ith particle number density. Say conserved charge means there is some current, right?
Right.
So gi mu is the current for that conserved charge, the number of particle number conservation, right? So explicitly the components are given here, right? The 0 component of gi 0 is ni, that's the number density of particles, and the vector, the spatial component is 0 in this frame because of isotropic, right? The particle current is not flowing in any direction.
So here you are considering each of the components have different global current, means corresponding
Yes,
to
because
symmetry.
only then the mui's are independent,
Right.
right? If the particle number is not conserved, right, then the mui's will not be independent.
Right.
So this gives you k equations. Right? You can convert this into mu's because ni's are functions of mu and t, mu I and t. Okay? So this you can write as a set of equations involving mu I and t. Okay? So in these variables, in terms of these variables, the k plus 2 variables, you have altogether k plus 2 equations because 2 equations were here and k more equations are coming from here. So now we have k first order equations in k variables and we can solve this given the initial condition. Is this clear?
So where we have used this equation of state for different components.
Oh, equation of state has gone in because this rho i's, right, will have to be expressed in terms of t and mu, right? So that's why the equation of state goes in. So otherwise you have new variables rho I, right, which you don't want. And pi's also, right? So all of these have to be re-expressed in terms of mu and t.
Can you please clarify one point is that this ni a cube means the conserved current whatever you consider, that is true for suppose you consider scalar particle, right? Where basically there is no such kind of global conservation law, so
Suppose
that
that
it
is
can
one,
give
yeah.
some conserved current. So for that case, how you will fix that mu value for the
It
scalar?
will be
particle?
0.
It will be 0.
Yes. If the particle number is not conserved, then the corresponding mu is 0. Right? That's the rule in statistical mechanics.
Right,
Right?
right. Like photon, which is
Exactly.
something. Okay.
So you will set mu equal to 0 for the scalar. Okay? In thermal equilibrium, out of thermal equilibrium, things will be defined as I'll discuss. But when you are there in thermal equilibrium, then you just set mu equal to 0.
Ashok.
Yes.
So, in the case where you were saying that you have electron and positron,
Yes.
in this case you said two mu equal or with some relations, and you have a global conservation for one of the. So you have a mixture of what you say, one condition on mu and one condition on the particle number. Is that correct? Or?
That's right. So when there is a global conservation, so I'll discuss this general case later. Right? That when not everything is conserved, only partially some combinations are conserved. Right? Like for E and electron and positron, right? The difference between the number of electrons and number of positrons is conserved. The sum is not conserved in thermal equilibrium.
Mu will be related.
Mu's will be related. Yes.
Then that will supply.
Exactly. Okay, so now let's look at the general case. Little more general case, not a fully general case. Fully general case I'll do in a few minutes. So consider a system with three components. A, B, C. And let's suppose that we have a process A plus B going to C plus C or vice versa. Okay, that A and B particles can collide to make two C particles. Okay, there is a scattering process like this. In this case, so we are again back to thermodynamics, okay, statistical mechanics. Forget about expanding universe. Okay, let's try to understand what we do in statistical mechanics in such cases. So in this case, Na, Nb and Nc are not separately conserved. Well, this process changes Na, Nb and Nc, right? It reduces Na by 1, Nb by 1, increases Nc by 2, right? Or vice versa. But of course, not everything is lost. Okay? Some combinations of these are still conserved. Okay? So one combination that is conserved is Na minus Nb. Let's call this N1 tilde. Right? Because you reduce Na as well as Nb in this process, or you increase Na as well as Nb. So Na minus Nb doesn't change during this process. Similarly, you can check that this combination Na plus Nb plus Nc, this is conserved. Total number of particles. Two particles lost, two particles gained in this process. Right? Total number of particles don't change. Is clear? This process will reduce Na and Nb by 1 each, but will increase Nc by 2. Right? So this is unchanged. So in this case, when you introduce a grand-canonical ensemble, the way we define the grand-canonical ensemble is that you introduce chemical potentials for the conserved charges. So log Q, when you define, is sum over all states of both systems let me just write e to the minus beta E, but plus beta mu1 tilde n1 tilde plus beta mu2 tilde n2 tilde. Okay. So you don't introduce chemical potential for Na, Nb and Nc. Instead you introduce chemical potentials only for the conserved charges, mu1 tilde and mu2 tilde. The other linear combination, which is not conserved, has no chemical potential. This is a generalization of the fact that if the particle number is not conserved, you set mu equal to 0. Right? Here it's not that nothing is conserved, some things are conserved. So for those you introduce mu, but for others you don't. But this you can rewrite as beta this is Na minus Nb plus beta mu2 tilde Na plus Nb plus Nc. Okay, so that sum to the minus beta E plus, let me write as beta mu A Na plus mu B Nb plus mu C Nc where mu A you can easily read out from here. That's the coefficient of Na. So that's mu1 tilde plus mu2 tilde. Mu B is mu1 tilde minus mu2 tilde. And mu C is just mu2 tilde. And with this understanding, you can write log Q as log QA plus log QB plus log QC. Okay. So because once you have written it this way, then you are just doing independent sum over the states of A, states of B, states of C. Right? Where the conservation laws have been hidden is the fact that mu A, mu B and mu C are not independent anymore. Right? The sum is independent. That's why you are writing it as QA plus QB plus log QA plus log QB plus log QC. Right? This is a product of three independent partial functions. But the mu's are related. Because three mu's are expressed in terms of two independent mu tildes.
So isn't mu A, mu B, mu C 0?
Pardon?
Mu A, mu B and mu C.
It's not 0. No. They are not 0. Mu1 tilde and mu2 tilde are arbitrary. Right? Some combination of them is 0. So what combination is 0? The mu A minus mu B minus 2 mu C. Sorry, plus 2 mu C. No, minus 2 mu C. This is 0. Right? From this, if you take mu A plus mu B, no, sorry, mu A minus mu B is 2 mu2 tilde. Minus 2 mu C is 2 mu2 tilde, that's 0. So this is one relation between the three mu's.
Mu A plus mu B minus 2 mu C.
Yes.
Mu A plus mu B
Minus 2 mu C.
say mu A plus mu B will give 2 mu1 tilde, right?
Yeah, but in mu B the sign or maybe reverse because you
Oh.
had
I see. So that I have to check. So mu B, mu2 tilde comes to minus. Yeah, you are right. Yes. So mu A plus mu B minus 2 mu C.
So in this energy expression, there is no interacting potential term.
No, we are not assuming that those you are all ignoring, right? So the partition functions are exactly what it was before, okay? Except that the mu's have been related. Because you don't have to do any new calculation. Those formulae that I wrote down, right, are still valid. Okay? It's just in those formulae, you will not think of mu1, mu2, mu A, mu B, mu C as independent, but only mu1 tilde and mu2 tilde as independent. Is this clear?
So if the equation was like a plus b is going to c, so what would be then
Yeah, so if it has a plus b going to c, this is still constant,
yes.
right? And you have to put a 2 here,
Yes.
right? That's what will be constant. Is this okay? So what we have done in this system is that we have reduced the number of variables by 1, right? What are the number of equations? Is it the same or reduced or increased compared to the earlier case? Earlier you had 3 conservation laws, number conservation and Friedman equation and energy conservation, right? 5. Okay, that was matching the correct number. So now how many equations do you have? Number of variables have reduced. Have the number of equations reduced, increased? Reduced. Why has it reduced?
Now the like instead of 3 conservation law, we have 2 conservation.
Yeah, so now instead of 3 conservation laws, you have only 2 conservation laws, right? So instead of having this, now what we have is a d dt of Na minus Nb times A cube is 0, because this is constant, and d dt of Na plus Nb plus Nc is 0. Pardon? A cube, thank you. Okay, so we still have the same number of equations as the number of variables. Okay, we reduce the number of variables and number of equations. And this is the general rule. Every time you have we lose a conservation law, you also lose a variable. The corresponding mu is gone. So you always have the same number of equations as the number of variables. Okay, and hence you can solve it. Okay, so let me discuss a general case, then I'll stop. So a general case will be k components and L conservation laws. Okay, with L less than or equal to k. Okay, L equal to k is a previous case where all are concerned, but in general L conservation laws. And we'll introduce these numbers n tilde L. These are the conserved numbers. Again, we are back to statistical mechanics, not cosmology for the time being. Okay, once you understand statistical mechanics, we'll go to cosmology. So some linear combination of the n's, ni's are conserved. So write them C L I N I. Well, these are some constants, known constants. Okay, that they determine which combinations are constant. And L runs from 1 to L. Pardon? I equal to 1 to k, because this sum runs over all the spaces of particles. right? Because each conserved charge is some linear combination of all the particle numbers, right? Just like here it was Na plus Nb plus Nc, right, or Na minus Nb. Right? Some of these could be zero, but in general it's some general linear combination of all the particle numbers, right? That's the expression for a conserved charge.
What does this small l signify?
Small l?
Yes.
Oh, small l is a label that there are L conserved charges, right? We have to use a label for those, right? So L equal to 1 is the first conserved charge, L equal to 2 is the second conserved charge, L equal to capital L is the LH conserved charge, right? That's what it means. Is this clear? So in this case, what we will do is that this mu exponential, instead of having sum over I mu I ni, beta mu I ni and the exponent, we will replace it by e to the power beta sum over L mu tilde L n tilde L. Because we introduce chemical potential only for the conserved charges. Okay, this sum runs over L values. Okay, so there are L independent mu tilde L's instead of K. But of course, this I can rewrite as e to the power beta sum over L sum over I. This sum over I runs from 1 to K, sum over L runs from 1 to L. And mu tilde L I just express like this. So C L I N I times mu tilde L. Without this, because this will be always there. So this I can write as e to the power beta sum over I equal to 1 to K mu I Ni, where mu I sum over L CLI mu tilde L. Okay, just rearrange the sum a little bit. This sum I took the sum over L inside, right? And whatever was multiplying Ni, I called mu I. Is this clear? So once you have written it in this form, then log Q is again sum over log Qi. Right? You don't have to calculate a new calculation, you can just use your old calculation. But the difference is that the mu i's are not all independent. Instead of K mu i's, we really have L independent variables, mu tilde L's. These are your independent variables. So now we can do cosmology. In cosmology now, of course, you will have these equations. But the number conservation equation, how many will be there? How many conservation equations will you get? L. Right? Because each of these are conserved. So the equations will be ddt of L cube times sum over I equal to 1 to K CLI Ni equal to 0 or L equal to 1 to up to L. So number of equations number of equations is L plus 2. These L conservation laws are these two. Variables are A, T. T is of course common because you are assuming thermal equilibrium. And then mu tilde 1 up to mu tilde L. That's L plus 2. Okay, so again we have the same number of equations as the number of variables. Okay, and hence we can evolve this. Is this clear? But I should emphasize that the most important aspect of cosmology is that these equations that we are writing are not valid universally. They are valid only in certain time domain. Because in certain time domain, some things may be conserved, some things may not be conserved. In a different time domain, okay, at higher energy or lower energy, what was conserved earlier may not be conserved now, or vice versa. Or what is conserved today may not have been conserved early in the history of the universe. So at every time slice, you have to decide which are conserved, right? Which are in thermal equilibrium. Okay, whether you should use independent energy conservation laws for different components or combined energy conservation law. Right? That depends on whether this is in thermal equilibrium or not. Right? You have to decide which are the conserved charges. Sometimes the number of conserved charges may change. Right? For example, if you have a particle-antiparticle pair, right, as we have been discussing, particle-antiparticle pair annihilates. Right? So, if the annihilation process is allowed, then the number of particles and number of antiparticles by themselves are not conserved. Right? It's only the difference that is conserved. But imagine that you are in some time domain, okay, where the probability of annihilation is small. Okay, the particle densities are so small that in one Hubble time, okay, one particle undergoes less than one annihilation. In that case, it's a good approximation to take the particle number to be conserved. Right? Because even though in principle they could annihilate, right, and pair produce, in practice that probability is very small. Okay? That annihilation rate is much lower than the expansion rate. Then it's more useful to think of each particle and antiparticle themselves as being separately conserved. Now this is of course a somewhat extreme case, but we will see various examples of this. Okay, that conservation laws which are valid today may not be valid at another time. Any questions? So next time we will see various examples of this changeover, right? What kind of changeover can take place when you have to actually change the equations. So we'll continue to